All right, this lecture is on specific heat capacity. It says it doesn't make a difference what temperature a room is. It is always room temperature. So the goals for this presentation are to, number one, you need to understand that mass and material affect how much an object's temperature will change. Number two, you also need to be able to figure out that the energy can be used to change the phase of an object. And number three, we're going to use equations to predict the final temperature of an object. Number one, specific heat capacity is the fact that different objects have different amounts of energy required to heat them. For example, you can use water, and water is very, very difficult to heat, whereas something like metal is very, very easily heated. It's the reason why if you take a pot, put it on the stove, and you have it just empty, it will heat up very, very quickly. But if you fill it with water, it doesn't heat up nearly as quickly. So different objects require different amounts of heat to raise the temperature by 1 degree. And that's our definition for specific heat capacity, is how much heat, how many joules are required to raise 1 kilogram of the material 1 degree Celsius or Kelvin. And it depends on the material itself. Water has a very, very, very high specific heat capacity. And that's a good thing because you're mostly water. Since you're mostly water, your body is able to maintain its temperature relatively easily. As a general rule, gases take very, very little energy to raise the temperature. Liquids take a little bit more, solids take the most, with the one exception being water. Liquid water is extremely high in its specific heat capacity. Alright, so the formula we have for specific heat capacity is Q, which stands for heat, is equal to M, which is mass in kilograms, and then you have the CP, that stands for specific heat capacity, and that's measured in joules per kilogram Celsius. Now you have to be real careful and make sure that the units of that match what you're trying to find, because sometimes it's in joules per gram, sometimes it's in kilojoules per gram, sometimes you have to check the units on that. That's what you really, really have to be careful of. And finally you have the change in temperature, and the change in temperature is the final temperature minus the initial temperature. So it's very important you realize that's not just one temperature, it's actually the difference between two of them. Also, you need to realize that Q can be positive or negative depending on whether heat is flowing into the system or out of the system. So if you're adding heat, the change in temperature, this will be positive and this will be positive. But if this is negative, because heat's leaving the system, this will be negative as well. So this works for both heating things up and cooling things down. In addition to that, you can actually use some energy to change the phase of an object. So what I mean by changing the phase is you're actually changing it from solid to a liquid to gas or something along those lines. Now, this type of transition requires much, much, much more energy than changing the temperature. And you'll see it's very similar. You have Q equals M, and then you have an L term instead of the CP. Now, there's no delta T because whenever you're changing the phase of an object, you're not actually changing the temperature at all. This L term is called the latent heat of transition, and it is an extremely large number. It takes a lot of energy to change the phase of an object. Much, much more than is required to change the temperature. And if you think, like, changing it from a liquid to a gas, you're actually trying to give the molecule enough energy that it can escape gravity and no longer be at the bottom of the cup, but then go off here and fly around the room. So it's a great, great deal amount of energy. So there are lots of transitions that we talk about when we talk about phase transitions. Some of them you're familiar with, like you've got solid to liquid is melting. Take an ice cube, put it on the counter, it'll melt. Take water, put it in the freezer, and it'll freeze. Okay, sometimes that's called fusion. That would be a liquid to solid. Gas to liquid, you usually see whenever you have a cold drink. If you have a glass of ice water, on the outside of it, you'll start to see some fluid. That is not fluid from the cup, but it's actually the air around it condensing. So it condenses the liquid on the outside of the cup. You also have liquid to gas. Okay, that's what happens when you boil something. The water itself is actually turning into that steam. Two that are not very common are gas to solid and solid to gas. Now you've probably seen solid to gas if you've seen Halloween stuff. There's dry ice that creates that smoke. It goes directly from a solid to a gas, and that's called sublimation. In addition to that, you also have gas to solid, and you generally don't see that very often, but you can make it to form pretty pure crystals. In addition to that, you should know that there are actually 6 phases of matter. They are solid, liquid, gas, and plasma, which you have learned in chemistry. But in addition to that, there are two that are very, very, very cold called Bose-Einstein condensate and fermionic condensate. Phase transition. So an object will, if you add heat over time, for example, if you just take something and put it on a burner, you'll see places where the temperature rise and places where it doesn't seem to rise at all. And so this is called a phase transition graph. So this is actually for water. If you see it, it's 0 degrees Celsius and 100 degrees Celsius, you'll see some things. Right here, where the objects are changing temperature, that means that they are in one phase. So it's changing temperature here, it's changing temperature here, and it's changing temperature here. So it's pretty easy to say, hey, this is when it's a solid, because that's when it's the coldest. Here's when it's a liquid, and here's when it's a gas. Now what's different about this is you actually have these two plateaus here. And remember earlier we said whenever you're changing phase, you're not changing temperature, and that's what's happening right here. When you take a piece of ice and you put it on a burner, or if you put it on the counter, all the energy goes into changing the temperature until it gets to 0. Once it gets to 0, all of the energy is used into breaking the bonds that make it a solid, so it's turning it into a liquid. And so that takes a lot of energy right here. And then what you do is you change the temperature. You change it from 0 all the way up to 100. And then once you get to 100, once again, you use all the energy to break those bonds as you go through and get to gas. Once you're here, then you can start to change the temperature. So whenever you lose heat by one system, it's gained by another. And that's just the same thing as the conservation of energy. Heat is a type of energy. Energy has to be conserved. So generally what you do is you can set it up like this. You can say the heat that is gained by one object, Q, is lost by another. And so you just set it up, mCp delta T minus mCp delta T. There are two types of questions like this. One in which they're the same, like you're mixing water and water. And there's another in which you're mixing two different things, like metal and water, or something along those lines. It is very important that you realize that the hotter object will always be the negative side, because it's the one that's going to lose the heat to the cooler side. And you'll see these as we work through some examples in this unit. So you should know, you should learn, you should memorize, you should be able to spout from memory how mass and material affect an object's temperature change. You should be able to talk about specific heat. You should be able to talk about the more mass, the easier it is, or the harder it is to change the temperature of. You should be able to say that energy can be used to change the phase, and you should be able to name those 6 changes of phase that we talked about, as well as the 6 forms of matter. You should be able to predict the final temperature of an object using equations, and you'll get more practice with that here in a little bit.